Welcome. In this lecture, we attempt to find the slope and deflection equations for a simply supported beam asymmetrically loaded by a point load using the double integration method and explain why it is not a feasible method in general. Let's draw a simply supported beam with an asymmetric point load and label accordingly. Let the reference coordinate be assumed at the left support A, from where the distance x of any cross section is considered. The reaction forces are shown at either supports. Now, the point load P divides the beam into distinct zones, region AC and region CB. The bending moment equations are written separately for these two regions. Using the double integration method, we therefore have a total of 4 unknown constants to be found out. For region to the left of load P, that is region AC, we write the bending moment equation and equate it to EI times the double derivative of deflection with respect to the length or distance. Integrating twice, we have two unknown constants C1 and C2. For region CB, following the same procedure, we again have two unknown constants which we call C3 and C4. For finding the four unknown constants, we need to have at least 4 boundary conditions. We hence apply the following boundary conditions. Deflection y at A equal to 0 for x equal to 0. Deflection y at B equal to 0 for x equal to L. Deflection y at C considering region AC equal to deflection y at C considering region CB. And finally, slope at C considering region AC equal to slope at C considering region CB. Applying the 4 equations as boundary conditions, we simplify them further and get 2 equations for deflection, one for each region. We write the results directly here to save space and time. You may wish to carry out the calculations separately and verify the results. Each equation for deflection so obtained is valid only in the region indicated. Now, if P is at the center of the beam, deflection y equals y max, that is at x equal to L upon 2. The deflection hence equals minus 1 over EI times P times L cube over 48. Minus sign indicates that the deflection is acting in a downward direction. This problem, although involving relatively simple geometry and loading, is obviously very tedious when solved by the method of double integration. Usually, therefore, this method is well suited only to situations where a single equation describes the entire deflected beam. Having seen the difficulties arising while solving for beam deflection in general using the double integration method, we hence resort to other convenient methods. For this course, we specifically shall use the adaptation of the double integration method, namely the Macaulay's method for solving the beam deflection problems, for which only one equation is necessary to describe the bending moment or the slope or deflection throughout the length, irrespective of the number of loads or regions present. In the next lecture, we shall use Macaulay's method to determine the slope and deflection curve of a cantilever beam subjected to multiple load types.